Hi, I'm Bob. Let's continue our solutions to the computer exercises for Chapter 14, Advanced Panel Data Methods. For the textbook, Introductory Econometrics, a Modern Approach, the 7th edition, by Professor Jeffrey Woodridge. We will do computer exercises 6 to 10 today. I will continue to use data to solve the problems. In the sixth exercise, we add the interaction term between Julian and time trend to the equation estimated in Table 14.2 point to see whether wage growth depends on Julian status. Estimate the equation by random and fixed effects and compare the results. We add the interaction term between the Julian dummy and the time trend variable to the model. We know that the time trend variable is perfectly collinear with year dummies. We could not add the time trend variable of the year to the model, but we could add the interaction term. It captures the difference in the wage growth rate between Julian members and non-Julian members. First, we estimate model with random effects. The coefficient estimate on the interaction term is minus 0.0155. Second, we estimate model with fixed effects. The estimate is minus 0.0157. It is almost the same as in the random effects. The difference is statistically significant at the 1% level. It implies that the wage growth rate for Julian members is 1.6% lower than for non-Julian members on average, holding the variables in the model fixed and controlling for individual fixed effects and year fixed effects. Let's do computer exercise 7. Use the state-level data on murder rates and executions for the following exercise. In Part 1, we consider the unobserved effects model. Eta t denotes different year intercepts or year fixed effects, and AI is the unobserved state effects. If past executions of convicted murders have a deterrent effect, what should be the sign of beta 1? What sign do you think beta 2 should have? Explain. Beta 1 should be negative, meaning more executions lead to a lower murder rate. Beta 2 might be positive. A higher unemployment rate results in more people living in poverty. Poverty begets hunger, and hunger begets crime. It might increase the murder rate. In Part 2, we used just data from 1990 and 1993 and estimate the equation from Part 1 by pooled OLS. Ignore the serial correlation problem in the composite errors. Do you find any evidence for a deterrent effect? We use the regress command in Stata to do the pooled OLS estimation. We find no evidence for a deterrent effect of past executions on the murder rate. The coefficient on the execution variable is positive and not statistically significant at the 10% level, with a tiny t-statistic of 0.49. In Part 3, we estimate the equation by fixed effects. We may use the first differencing because we only use 2 years of data. Is there evidence of a deterrent effect? How strong? Using the fixed effects time demeaning approach or the first differencing method, we obtain the same estimate for the execution variable. For 2 years of panel data, the first differencing and the fixed effects estimates and standard errors are identical. It is minus 0.104. Its usual standard error is 0.0434. The t-statistic is minus 2.39 and its p-value is 0.021 against a two-sided alternative. It suggests a deterrent effect of past executions on the murder rate. One more execution is estimated to reduce 1 murder per million people per year after holding the unemployment rate fixed and controlling for the state fixed effects. The effect is statistically significant at the 1% level. In Part 4, we will compute the heteroscedasticity robust standard error for the estimation. In Part 2, we use the variance-covariance matrix option to specify the heteroscedasticity robust standard errors. We can compare the results in a table. We find that the robust standard error for the execution variable is smaller than the usual standard error, but it is still not statistically significant at the 10% level. In Part 5, find the state that has the largest number for the execution variable in 1993. How much bigger is this value than the next highest value? We use the summarize command with the detailed option to get information on the execution variable. We can find the largest 5 values in the sample. The largest is 34, and the second largest is 11. It is 23 smaller. Since the state with the largest number of executions is Texas, we drop it in Part 6 to estimate the equation using the first differencing method. Compute the usual and heteroscedasticity robust standard errors. Now, what do you find? What's going on? We find that the estimates for the execution are statistically insignificant at the 10% level using the usual standard errors or the robust standard errors. It implies that Texas is an inferential observation. In the first differencing estimation, execution has a deterrent effect on murders only when including Texas observation. In Part 7, we use all 3 years of data and estimate the model by fixed effects. Include Texas in the analysis. discuss the size and statistical significance of the deterrent effect compared with only using 1990 and 1993. We use all 3 years of data and estimate the model by fixed effects using the xtreg command and the fe option in Stata. We store the results and compare them in a table. We find that the execution no longer has a significant deterrent effect on murders using all 3 years of data. The estimate is minus 0.138 with a standard error of 0.177. The t-statistic is minus 0.78 and its p-value is 0.436 against a two-sided alternative. Let's find answers to computer exercise 8. We will do a fixed effects version of the first differencing done in computer exercise 11 in chapter 13. The model of interest is as follows. In part 1, we will estimate the model by pooled OLS and report the usual standard errors. What are the estimated effects of the spending variables? Obtain the OLS residuals, new IT head. We estimate the model with pooled OLS and then use the predict command to save the residuals. The estimate for the current spending variable is statistically insignificant at the 10% level. The estimate for the lagged spending variable is 9.05, and it is statistically different from 0 at the 1% level. It suggests that next year's mass passing rate will increase by 0.9 percentage points if the spending this year increases by 10%, after controlling for enrollment, poverty rate, and year effects. The mass passing rate in the sample is from 7.6 to 100 percentage points. In part 2, is the sign of the lunch coefficient. What you expected. Interpret the magnitude of the coefficients. Would you say that the district poverty rate has a big effect on test pass rates? The lunch variable is the percentage of students in the district eligible for the school lunch program. It is a good measure of the district-wide poverty rate. Its value is from 0 to 91.27 percentage points in the sample used in the pooled OLS estimation. The estimate is minus 0.407, and it is statistically significant at the 1% level. A 1 percentage point increase in the poverty rate is estimated to decrease the mass passing rate by 0.4 percentage points, holding spending, enrollment, and year effects fixed. It is an expected and pretty large effect. In part 3, we will compute a test for AR1 serial correlation using the regression of residuals on the lag. We should use the years 1994 through 1998 in the regression. Verify that there is a strong positive serial correlation and discuss why. The simple regression gives a slope estimate of 0.5, and it is statistically significant at the 1% level. It is strong evidence of positive serial correlation. We know that if the composite error term nu contains the fixed effects ai and the idiosyncratic error mu it, then the correlation between adjacent composite errors will be positive. Here is the proof. The positive slope coefficient in the AR1 regression implies an unobserved fixed effect in the mass passing rate model. We estimate the equation by fixed effects in Part 4. Is the lagged spending variable still significant? The lagged spending variable is still statistically significant at the 1% level, with a t-statistic of 2.96. The estimate is 7, lower than that by the pooled OLS. There is still evidence of a lagged spending effect on the mass passing rate after controlling for unobserved discrete fixed effects. In Part 5, why do you think in the fixed effects estimation, the enrollment and lunch program variables are jointly insignificant? We find that they are individually insignificant, and we use the test command to perform an F-test for their joint significance. The F statistic is 0.73 and its p-value is 0.48. They are jointly insignificant at any conventional level. The reason is that they have little variation over time. The estimates are not precise after the time diminishing within transformation. In Part 6, we define the total or long-run effect of spending as theta equals gamma 1 plus gamma 2. Use the substitution gamma 1 to obtain a standard error for theta hat. First, in theta, we can get the standard error for theta directly using the lincom command. We type lincom followed by the sum of the two spending variables. The long-run effect is 6.59 and its standard error is 2.64. Second, we can use the trick to obtain the standard error for theta. We write gamma 1 in terms of theta and gamma 2 and substitute for gamma 1 in the model. We generate a new variable z equal to the lag log spending minus the log spending. We regress mass on year dummies, log spending, z, log enrollment, and lunch by fixed effects. The coefficient on the log spending is theta. We obtain the same estimate and standard error for theta as using the lincom command. The estimate is 6.59 and its standard error is 2.64. The long-run effect is statistically significant at the 5% level. Let's solve computer exercise 9. The dataset contains information on participant-directed pension plans for U.S. workers. Some observations are for couples within the same family. So this dataset constitutes a small cluster sample with cluster sizes of 2. In Part 1, we ignore the clustering by family and use OLS to estimate the model. The variable of most interest is choice, which is a dummy variable equal to 1 if the worker has a choice on how to allocate pension funds among different investments. What is the estimated effect of choice? Is it statistically significant? The estimated coefficient is 11.74 and its standard error is 6.23. The t-statistic is 1.88 and its p-value is 0.061 against a two-sided alternative. The effect of choice is statistically significant at the 10% level. In Part 2, are the income, wealth, stock holding, and IRA holding control variables important? Explain. They are individually insignificant, and we use the test command to test for the joint significance. The f-statistic is 1.03 and its p-value is 0.42. They are jointly insignificant at any reasonable level. These control variables are not important. The estimate for the choice effect drops slightly to 11.15 without these control variables. In Part 3, we will determine how many different families are in the dataset. The variable ID is the family identifier. We can use the codebook command to find information on the ID variable. There were 171 unique values. It means there were 171 different families in the sample. In Part 4, we obtained the standard errors for OLS that are robust to cluster correlation within a family. Do they differ much from the usual OLS standard errors? We use the variance-covariance matrix option to specify the standard errors robust to cluster correlation within families. The robust standard error for the choice variable changes slightly, and the statistical significance is almost unchanged. It is not surprising because there were only 23 families have couples in the sample, and the family cluster structure is accounted for. For the rest families with one family member in the sample, their cluster standard errors will be similar to the usual standard errors. In Part 5, we will estimate the equation by differencing across only the spouses within a family. Why do the explanatory variables asked about in Part 2 drop out in the first difference estimation? Those variables are constant within a family. The differencing between the couples within a family will eliminate the family constant variables. In Part 6, are any of the remaining explanatory variables in Part 5 significant? Are you surprised? We use the family observations with couples. To keep those observations, we use the by_sort command followed by the family ID. We keep the families with couples in the sample. Underscore capital N is the total number of observations within a family. We can use the browse command to see the structure of the data. Some couples are females and males, but some are the same gender. We set the panel variable family. Within each family, we set the gender order, male followed by female. We can use the capital D operator to create the first difference variables. All the explanatory variables in the first difference equation are not statistically significant at any reasonable level. Because the sample size, 23, is small and there is little variation in the first difference variables, the estimates are extremely imprecise. We can compare the estimates by first differencing with the estimates by fixed effects. They are identical because of two observations within each family. Now, let's find the solution to computer exercise 10. We are interested in estimating the following model. In part 1, we estimate the above equation by pooled OLS. The estimated equation is as follows. The estimate for the concentration variable is 0.36. If it increases by 0.1, the AFS are estimated to increase by 3.6%. In part 2, we compute the usual OLS 95% confidence interval for beta 1. Why is it probably not reliable? We will compute the fully robust 95% confidence interval, compare it to the usual confidence interval, and comment. We use the variance covariance matrix option to specify the standard errors robust to heteroscedasticity and serial correlation. The fully robust confidence interval is wider than the usual confidence interval because the robust standard error is larger than the usual standard error. The usual standard error is not reliable due to possible serial correlation within each airline. In the presence of the airline root fixed effects, the composite error term must have a serial correlation. In part 3, we will describe what is happening with the quadratic in log distance. In particular, for what value of distance does the relationship between log fare and distance become positive? We can figure out the turning point value for log distance by equating the first derivative to 0. The turning point is 79.51 miles. After that point, the fare increases with distance. In part 4, we will estimate the equation using random effects. How does the estimate of beta 1 change? The random effects estimate of beta 1 is 0.209. We estimate the model by fixed effects in Part 5. The estimate of beta 1 is 0.169. We can compare the estimates in a table. We find that the random effects estimate of beta 1 is closer to the fixed effects estimate than the pooled OLS estimate. The reason is that the zeta hat for the random effects estimation is 0.84. It is closer to unity, and it means the variance of the unobserved fixed effects is relatively large compared to the idiosyncratic error. In Part 6, we will name two characteristics of a route other than the distance between stops that are captured by the fixed effect AI. Might these be correlated with concentration? The characteristics of the airplanes used in the route and the features of the cities between the airports are the time constant factors captured by the fixed effects of AI. They could be correlated with the key explanatory variable concentration in the model. In Part 7, are you convinced that higher concentration on a route increases airfares? What is your best estimate? Yes, higher concentration on a route will increase airfares. The most reliable estimate is 0.169 from the fixed effects estimation. It is statistically significant at the 1% level, and the fixed effects approach has controlled for the unobserved route-specific factors that could affect both the airfares and concentration. The fixed effects estimate is a consistent estimate of the concentration effect on the airfares. Thank you very much for doing the computer exercise with me. See you soon. Thank you for watching this video and subscribing to my YouTube channel. See you next time.